Okay, so we're recording, and let me give you a moment to copy this example down. Okay, all right. So we have here two vectors that are in R2 space, and I want to know, are the vectors linearly independent? And I've not even formally taught you about the definition of linear independence yet, but looking at the two vectors, do you think the vectors are linearly independent, or do you think they're linearly dependent? What are your thoughts? Okay, Justin thinks they're dependent. Nema thinks they're dependent. Well, all right, if Nafani thinks dependent, if you think they're dependent, then why do you think they are dependent? Who can maybe chat it out, or you could verbally answer too. That's right, Hung. They are multiple. Those vectors are multiples of each other. That's right, Eleanor. Multiples. Yes, Nema. And so in your heart or soul, I guess, you have an idea of what independence means. Okay? But let me go ahead to the solution here, and I'll be a little more formal. So, well, I mean, clearly the second vector is equal to twice the first vector. If you multiply v1 by 2, you're going to get the v2 vector. Okay, so because of that, the set of vectors is linearly dependent. Linearly dependent. Okay, so let me give you a moment here to copy that. And let me know if there are any questions. Christopher, I'm glad you're here as well. I saw your email. I'm glad that second alternative worked for getting in here. Wonderful. And Ariana as well. I'm glad you're here too. Hung, I should get you a virtual candy bar. That's what I should do for your help there. And Nema. But Hung mentioned the website, and so you know. I don't know if I have that. I don't know how to do that, you know. All right, thanks, Hung. Okay, so All right. Well, now there's another way to think about. We see this was an easy problem. We had two small vectors, and it was you could easily see that the one vector that was that the vectors the one vector was a multiple of the other vector. But what if you had four vectors or five vectors? How would you know if the vectors are themselves linear, the set of vectors is linearly independent or dependent? Well, we have to gravitate to a little bit more formal definition. But the formal definition relates to this. The solution, if we were to try to solve this equation here, and what kind of equation is this? This equation here? What kind of equation is that called in linear algebra? That's right, Benjamin. That's a vector equation. The solution to the vector equation, and when I say solution, I mean x1 and x2, is non-trivial. X1 equals -2 and x2 equals 1. That makes sense because if 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 V2, since V2 equals 2 times V1, that means that -2 times V1 plus V2 equals a zero vector. And so this vector equation here, okay, has a non-trivial solution for x1 and x2. If the vectors were linearly independent, what would x1 and x2 have to equal? If the vectors were to be linearly independent, then x1 and x2 would have to equal what? They'd have to equal both zeros. That's right, Benjamin. That's right. So given this, then, a little example here that hopefully, I hope it makes sense to you. We can then get to a general definition. So basically, if the vectors are linearly dependent, then there is a non-trivial linear combination of the vectors that will add up to the zero vector. If the vectors are linearly independent, then the only combination of vectors that would add up to the only linear combination of vectors that would add up to the zero vector would be where all your coefficients are zero. So let me go to the book here. One moment, and bring this up. Okay, so this is section 1.7. These are the formal definitions of linear independence and linear dependence. So we say that a set of vectors is linearly independent if the vector equation there has only the trivial solution. Okay. However, the set of vectors, and the trivial solution means x1 equals 0, x2 equals 0, x3 equals 0, and so forth. All the x's equal 0. The set of vectors, however, will be linearly independent if there's a linear combination of the vectors that equals 0, but not all of the weights equal 0. In other words, one of those weights is not equal to 0, at least one. Equation 2 is called a linear dependence relationship among the set of vectors when the weights are not all 0. When the weights are not all 0. Okay. Are there any questions on that definition? Okay, well then let me go ahead. Let's go ahead and get to another example then. Let's get to another example. Okay, let's look at this example. And let me give you a moment to copy this example down. I'm glad Justin's here as well with us. Wonderful. I saw your email. Very good. Okay, so let's see here now. Let's take a look here with this. So for this problem, it's less obvious if the set of vectors v1, v2, and v3 are linearly independent or linearly dependent. Okay. So for linear dependence to occur, that really means one of the vectors would have to be able to be a linear combination of the other two vectors. And sometimes you can figure it out just by looking at the vectors. There's a few problems in your homework for section 1.7 where they give you some vectors, and you can establish a dependence relationship without too much difficulty. But here, not quite so easy. In other words, if the vectors were linearly independent, v1 would equal something, some value times v2 plus some value times v3. And these values can't both be zero, these coefficients. And in fact, they would both be, in this case, they'd both be like non-zero coefficients. But offhand, I don't know if anybody can guess, what if they tried, if they could guess values. Okay, you might be wondering, what. So, we don't want to spend all day guessing. And in fact, the answer may be they're linearly independent. So how are we going to start? How are we going to start this problem? It's a little bit like the movie. I don't know if you've seen the movie I, Robot with Will Smith. How many have seen that movie? It's where he's trying to figure out who murdered his doctor. I don't know. Is that movie, Andres? It might be a little bit old for you. I don't know. But at any rate, you know, he keeps like in order to solve it, to solve the mystery, he has to ask the right questions. And this is a little bit like here. In order to start, we have to say, well, what are we going to start with? Well, let's start with the definition of linear independence. So on that note, here's the question we have to ask. Does this vector equation, x1 times v1 plus x2 times v2 plus x3 times v3 equal to 0 vector, does it have only the trivial solution? Okay, that's what we need to find out. So we have to solve this vector equation for x1, x2, and x3. Are there any questions up to this step here? Please let me know if you have any questions. Okay, well, we know that the vector equation is then going to lead to a system of equations that has to be solved. So we'll set up the augmented matrix, and then we proceed forward. But let me slow down a little bit. Augmented matrix, of course. Are there any questions up to here? May I go to the next page? All right, Eleanor's good. Name is good. Okay, well, we're gonna do the row operations to reduce this. Okay, and what's that one called there in the first row? What do we call that one? What's the term for that? We're going to use that. Good, everybody. Good. It's a pivot. We're going to use that pivot to produce zeros in those two spots where the 2 and the 3 are. So, okay. And it can be shown in the interest of time. You can do the row operations, and this is going to be your reduced row echelon form of your augmented matrix. And so it turns out that you have a non-trivial solution, okay? Because you have a free variable, okay? And x2 equals negative x3, and x1 equals 2x3. Make sure that isn't. Okay, so All right. For some reason in my email, it looks like it sent that first email I sent you out again. I don't know why. Shouldn't do that. It's the second one that had the link that works. So at any rate, you know that. So okay, well, therefore, this set of vectors is linearly dependent. It is linearly dependent. Because the only solution, if this set of vectors v1, v2, and v3 were linearly independent, x1, x2, x3 would give us 0. Okay, and so, but that didn't happen. But just to sort of make the point clear, for example, if you were to let x3, your free variable, if you were to let it equal 5, then x1 would equal 10, and x2 would equal -5, and then 10 times the first vector, v1, minus 5 times the second vector, v2, plus 5 times the third vector, v3, would equal the 0 vector. And you can check that out. You can check that out. You'll see it's true. Similarly, we could say that v1 is equal to 1/2 v2 minus 1/2 v3. I think it's a little easier to verify. I mean, when you get down to here, verify it. Look at your vectors v1, v2, and v3 and see if that is just kind of verify it for yourself. And let me know when you've checked it. But let me give you a moment here to catch up. Okay, so check this out. Does this relationship between the vectors v1, v2, and v3 check out? How many are maybe have just take a moment to check and see if it's true. In other words, does the vector 1, 2, 3 equal 1/2 the vector 4, 5, 6 minus 1/2 the vector 2, 1, 0? I'm just kind of curious if we might have a few students who will check that. I'll sleep better knowing you've checked that. Okay, Hung confirms it. And might we have one more person? Thank you, Hung. Okay, thank you, Naima. Thank you, Eleanor. Okay, great, great. So this is really, you know, it's a fascinating concept. Let me go ahead and use the whiteboard for a moment. I want to show you something. Are there any questions before we move on? Okay. Let me bring up the whiteboard. Okay. So okay, one moment. Got to watch out for that eraser. Really should give you a warning, you know, that eraser button. Like, do you really want to erase? Okay, so here are two vectors. We'll call them E1 vector and E2 vector. And I'm wondering, is this set here, is this set of vectors right here, I mean, it's the only set there, is that set linearly independent? Is that set of vectors linearly independent? Let me ask you this, where do these vectors live, E1 and E2? What space do they live in? Is it one-dimensional space, two-dimensional space, three? All right, two-dimensional space, or R2. Very good. So I'm wondering, are these two vectors linearly independent? In other words, if I were to think about this vector equation, and we know that 0, 0 will work, right? This is certainly true. But are there any other weights that would work to make this equation true? Or is 0, 0 are those the only weights that will work? Yeah, absolutely. That's right, Haley. That's right, Nafani. There's no other linear combination of the E1, E2 vectors that would give you the 0 vector. So the answer is yes to this. And I tried to pick, easy vectors. By the way, do the vectors E1 and E2, do they span R2? Do these two vectors here span R2? In other words, can any vector in two-dimensional space be written as a linear combination of E1 and E2? Good, that's yes. So in fact, E1 and E2 form what's called a basis for R2. When you have vectors that span a space and the vectors are linearly independent, that forms a basis for the space. That's something we'll get to later on. Okay, that'll come up later on. But just want to mention that. All right, fine. All right, let me do another example now. Let's say you have 1, 0, 0, 1, and 0, 0. Okay. Is that, and I'll abbreviate this, is that linearly independent? All right, I'm getting some quick answers from Andres and Eleanor. And I really should write linearly. I don't know. I don't like to abbreviate too much. Hold on here. The words are so important, I don't want to abbreviate them. Linearly independent. Well, all right. So if the vectors are, if the answer is no, two people think no, one person thinks yes. Let's see. Two people think yes, they are linearly independent. Okay, so it's a good discussion. So let's set up the vector equation here. Shoot. I have to bring it down here. I guess I can bring that over, can't I? All right, hang on. One moment. Hold on. I don't like to have, I prefer to work across, so. Okay, so let's continue. Learn new things every day. All right, so for the people that said no, that think no, that this set of vectors is not linearly independent, that this set of vectors is linearly dependent, could anybody who thinks that, could you show that by putting in some numbers here? And I think the whiteboard is shared, so do we have a volunteer who will fill in some numbers there? Okay, Eleanor. Eleanor's suggesting this. Eleanor's suggesting 0, 0, and 1. Very good, Eleanor. That means x1 is 0, x2 is 0, but x3 is 1. Okay, so previously, right, when we had, for the first example, we had x1 equals 0 and x2 equals 0. But now we have, in this second example, we have 3 vectors, and look, we have a non-trivial solution. x3 equals 1. I mean, we found a non-linear, I want to be careful, we found a non-trivial linear combination of the vectors that will equal the 0 vector. So the answer is no. The answer is no. Okay. Are there any questions on that? Okay. Who's more comfortable with that now? I did. The few people said that thought the vectors might be. Okay, good, good. Let me give you one more. Thank you, Lewis. Nafani, how are you feeling about that? Nafani, are you feeling okay with that? And good. And Benjamin, feeling good? All right. Let me give you one more here. Great. All right. What about this? What about this? Because I want to give you a little time to work here. What if you had 1, 0, 0, 1, and 2, 3. Okay. And I'll call this E1, E1, E2, and I'll just call this like a vector V3. Just for, you know. What do you think about this? What do you think about this set of vectors here? Is that set linearly independent? Eleanor thinks yes, and I appreciate all responses. Benjamin thinks no. Okay, we got a difference of opinion. Okay, now Eleanor's back. She's thinking dependent. She's changed her mind. That's okay. You can change your mind. Abby thinks no. Okay, well, all right, Abby thinks no. Well, then can somebody maybe write in here, you know, can somebody write in some values there for x1? You know, this is x1, x2, x3. People are saying the answer is no to this. Do we have any volunteers? You can do it on the whiteboard. Andres thinks dependent as well. Oh, okay. Okay. Somebody's writing. That's good. We got a -3. Can we? Okay. That's excellent. That's excellent. That's correct. So this set of vectors is linearly dependent. E1, E2, E3. Very good. And who wrote? I mean, I thank you, volunteer, who wrote that in. Who was our volunteer? Volunteer. And you can be anonymous. You don't have to say. It's okay. All right. Thank you, Benjamin. So what happened here? We had, we were doing so well with this. We had, E1 and E2. Those were, those vectors are linearly independent. But when we add in this third vector, it doesn't work anymore. The set of vectors collectively becomes a linearly dependent set. Why do you think that happened? Why do you think that happened intuitively? I mean, these three vectors live in R2 space, right? Two-dimensional space. But I mean, is there any third vector that I could add to this set that would preserve linear independence of the set? That's right, Benjamin. The answer is no. In other words, we have more vectors than the dimension of the space. We have more vectors than the dimension of the space. And this promotes what's called Theorem 8. This relates to Theorem 8 in your ebook. Does that make sense? I mean, it's going to take you a little time to get comfortable with it, but okay, are there any questions? All right, I'll stop the recording.